Hello, everyone. Thank you for coming. My name is Nao Kyoguchi, and he is Jin Hase. We are with SUSE Technology, a group company of Fujitsu. Today, we'd like to introduce emerging composable disaggregated infrastructure and also explain what we are doing to integrate CDI with SUSE Launcher and RKE2. Today, generative AI opens the age of AI. As a result, enormous computational resources are required. That needs lots of power. That needs lots of power to operate. On the other hand, realizing a sustainable world is an urgent issue for us. So we are always expected to reduce power consumption. This means we are expected to satisfy high performance and power saving simultaneously. So to cope with these conflicting requirements, composable disaggregated infrastructure is expected. CDI is emerging new server architecture. It disaggregates existing servers into separate components, like this. And each component is connected to PCIe or CXL switches. And this works as a resource pool. And by configuring this switch, By configuring this switch, user can create custom-made server by software definition. We call these bare metals as composed bare metal. So CDI is composed of resource pool and CDI manager. And in resource pool, all components are connected to PCIe or CXL switches. And CDI manager controls the switches so as to create composed bare metals. And it also has CDI API, and operator or Kubernetes can access this API. Once these composed bare metals are created, user can install any operating system on top of this bare metals. Because composed bare metals looks like normal physical server, so user can install any operating system. The first value of CDI is it can dynamically scale servers up and down depending on the workload. We call this feature dynamic device scaling. Let's consider AI inference system, for example. When there are lots of inference operations in daytime, CDI can attach GPUs and provide higher performance. And when there are few inference operations at nighttime, it can detach GPU and save power consumption. Using CDI, user can balance high performance and power saving. The second value of CDI is it is cost saving. CDI creates custom-made bare metals on demand, only using necessary components. And when servers are not used anymore, a user can return those servers to resource pool. And the components are used for other purposes. So CDI can minimize unused resources and reduce total cost. Let's introduce a primary CDI system. It consists of 4 components. The main component is fabric switch for PCIe and CXL. And second component is chassis for PCI cards and CXL memories. And we also need a compute node with CXL ready Intel or AMD CPUs. These servers are connected fabric switches through HBA card. And finally, we use management server to control fabric switch and chassis. Actually, we have released CDI V1 last year, and it provides GPU and I/O pooling. We plan to provide CDI V2 in 2025 in Europe. It provides CXL 2.0 memory pooling, dynamic device scaling, multi-tenancy, and multi-cluster. Finally, we will provide CDI V3 in 2027. It provides memory sharing and CPU pooling. We are developing primary CDI focusing on these 3 points. One is automatic optimization to balance high performance and power saving. CDI can scale up and down composed bare metals based on workload, so it achieves high performance and power consumption, power saving simultaneously. And second point is we use de facto standard open technologies. For example, dynamic device scaling is developed in Kubernetes upstream communities, so any operating system can use this technology. And finally, we provide secure and stable operation by cloudization and rich RAS function. We introduced cloud technology to this server, so we can provide multi-tenancies and multi-clusters. And our RAS function firstly detect failure of parts and easily separate it.
Failover. By separation, you mean automatic failover?
Right now, it's automatic, but user can know which part is failure. So manually,
Manual failover.
yeah,
Okay.
and replace it, manually replace it. In the future, we will provide automatic replace function. And so CDI is quite a new architecture, so we believe open development is essential to widely spread the CDI architecture. Right now, we are developing with OSS communities. For example, we are developing dynamic device scaling function using DRA, CDI operator and DRA with Kubernetes communities. And we are also developing CXL functions with Linux kernel community. And moreover, we will develop future CDI manager based on Open Fabrics Alliance Sunfish architecture. Okay. I introduced the mechanism of dynamic device scaling. It uses the technology of Kubernetes. Actually, we are developing CDI operator and expanding dynamic resource allocation DRA function and Kubernetes scheduler. We plan to use dynamic device scaling in two scenarios. One is operator assign the number of GPU manually to CDI operator, and CDI attach GPU. And second scenario is using pod autoscaler. When pod autoscaler increase pod, and there are no available GPUs, in that case, Kubernetes scheduler requests the CDI operator to attach GPUs. So today, I will show the demonstration of prototype. Okay. This is a system diagram. And when demonstration progress, this diagram shows which part is working. And this console is a Kubernetes console controlling Kubernetes control plane. And this screen shows the log of CDI operator. And this window shows the status of this pod. Okay. And in this scenario, in this demonstration, we show the scenario number 2. But we don't use the pod autoscaler. And instead, manually, we start the pod. Okay? So okay. This operation shows there is only worker node number 0. Only one worker node. Actually, control plane is working on the same worker node. And now, this shows there is no GPU, but NVIDIA DRA driver is working. This operation shows there is no GPUs. Okay? Okay. This is a YAML file we are just starting. Okay. And now we start the pod. And right now, the pod start, but there is no GPU. And this pod requires one GPU. So there is no GPU, so the status is just pending right here. And this shows the reason why pod is pending, because there is no GPU. So now a scheduler requests CDI to CDI operator to attach GPU. And now GPU is attached. And after GPU is attached, DRA recognizes the GPU, and scheduler starts the pod. And DRA plugin connect pod and GPU. And finally, pod status become running. That is a prototype. Right now, we can attach the GPU and start pod. And we are discussing to implement this in the upstream. However, However, we have still some problem. When we detach devices without removing program on devices, it will collapse workloads. Especially, it is fatal for programmable devices such as GPU and data processing unit and infrastructure processing unit. For example, there are two nodes. And in this situation, user want to remove node number 1 for power saving. In this case, user have to move port number 1 before detaching GPU. So we are discussing these problems with community people. Okay, so from now, Hassan will explain what we are doing to integrate these technologies with SUSE software.
Okay. Next, I explain our support plan for SUSE products in CDI version 2. Our target product is SUSE, RK2, and Launcher. And SUSE user will be able to run SUSE and RK2 on composed bare metal, and will be able to leverage CDI features. And regarding SUSE, we will be able to use CX memory pooling. And regarding RK2, we will be able to use GPU dynamic device scaling feature. And in addition, regarding Launcher will allow user to choose CDI as infrastructure provider when user install RK2. And users can install RK2 clusters on CDI system from the existing Launcher user interface, and can realize efficient use of resources by CX memory pooling and dynamic device scaling feature. Next, I will explain how CDI system actually works. This page shows how to create a composite bare metal. And this is done automatically when using Launcher. However, I explain the procedure in case of create a composite bare metal manually. To create composite bare metal, at first, we check the list of resources in the resource pool. To do this, we use CDI control command, especially CDI control resource list command. This command, by using this command, we can check the list of resources in the resource pool. And then allocate resources to be used for composite bare metal creation in the group. And the group is a collection of resources set aside to create a composite bare metal. And composite bare metal is created from the resources in the group. So to do this, we use CDI control group modify command. And then we create a composite bare metal with any configuration from resources in the group. And to do this, we use CDI control machine create command. And in this case, we specify machine configuration YAML file. This is a machine configuration YAML file. And we specify group name, machine name, and which resources is combined to the server. In this case, one compute server and one GPU and one storage is. Yeah, so we can create a composite bare metal server. And next, I will explain the procedure to install operating system on the created composite bare metal. This procedure can also be automated, but here is an example of a manual installation. First, we register the OS image in the control appliance, which is in CDI management server. To do this, we use CDI control image at command, and we specify OS image. In this case, we specify SUSE 15 image file. And then we check the name of the storage in the composite bare metal. So we use CDI control resource list command, and we specify the name of composite bare metal. And if we if we execute this command, we can check the resources of the composable bare metal, and we can see SSD 0 is target storage. And then we install the registered OS image to the storage confirmed in the second procedure. And we use CDI control resource install command, and we specify the target storage name, in this case SSD 0, and target OS image name, in this case /15 image file. So we can install any operating system into the composable bare metal. Here is a screenshot of the actual installation of /15 SP4 on the composable bare metal. First, we create a composable bare metal by combining one server with one GPU and one SSD by using this command. And then we confirm that this GPU is NVIDIA A100 model. When create composable server, we specify GPU 0, and we check the GPU 0 detail information, and we can know GPU 0 is corresponding to A100 GPU. And then we install /15 into this composable bare metal server. And then we can look this OS image has been installed correctly. And then we can confirm that A100 is recognized by LSPCI in /s on the composable bare metal server. This is LSPCI result. We can see A100 is connected to the composable bare metal server correctly. And next, I will explain one of the key concepts in CDI, tenant. Tenant is a concept which separates network physically and don't interfere with each other. And this is similar concept to VPC in AWS. However, please note that CDI separates it at the physical network level by using port VLAN. And the resources in a resource pool can only belong to one tenant. And left diagram shows the concept of the tenant logically. And there are two tenants, tenant 1 and tenant 2. And there are also resource pool. And the user create two tenants and so just a moment, please. And any resources from the resource pool can belong to either tenant, and a resource belonging to a tenant cannot interfere with another tenant. And this is useful when multiple companies are using a CDI system at the same time. And each company then allocates resources to its tenant on demand and pays for the amount of resources used. This is especially important when CDI is delivered like a bare metal cloud. And right diagram shows the concept of a tenant physically. The network card connected to PCI switch, and this belongs to a tenant, and it's connected to server within that tenant. And in this case, green part shows tenant 1. So this server and this network card belong to tenant 1. And blue part shows resources belonging to tenant 2. So this server and this network card are belonging to tenant 2. And in this case, we use port VLAN, and port VLAN allows for physical network isolation between tenants. This is a concept of tenant. And I will explain an example of creating an allocated cluster within a tenant. First, the user could create a tenant. At this point, no resources exist in the tenant. And to do this, run CDI control tenant create command. Next, create cluster within the tenant we just created. To do this, we use CDI control cluster create command, and we specify a configuration file that describes the cluster type, number of nodes, and etc. And if we use CDI control create command, this command is create group and obtain resources and create composable server and installing allocated cluster. All of these tasks are done automatically by using this command. So we can install allocated cluster on the composable metal in the tenant by using this command. And finally, this is how to combine with Rancher. And this is a use case of applying CDI to a system with various resource utilization between day and night. And there are two systems. First is AI inference system, and second is machine learning system. And in daytime, there are many people. So AI inference system required many GPUs. So in this case, CDI attach many GPUs into the AI inference systems automatically. And then in night time, there are few people, so AI inference system don't require many GPUs. And regarding machine learning system, we would like to run machine learning in night time. So these GPUs are moved machine learning system automatically. And then in case of we don't require any GPUs, we can return these GPUs to resource pool, and we can save power consumption. And this resource moving will be done automatically depending on workload. And in this case, Rancher install RK2 on the composable server. So existing Rancher user will be able to use CDI as an infrastructure provider. And this is a last page. We have an exhibit for CDI, so if you are interested in CDI, please come here. Okay, that's it. Thank you.
Any questions?
Yes, you are in discussion with the community about this CDI
Yes.
manager.
Mm-hmm.
Are the sources, are they publicly available on GitHub or for CDI, CTL command and CDI manager?
CDI manager. Actually, CDI manager is right now it's proprietary development, and but in the future we have a plan to develop in a community of Open Fabric Alliance, and we are just discussing with some fish communities. So maybe CDI V2 or V3, maybe V3. We can provide the OSS version of CDI manager.
Okay, is the coding internally available in Fujitsu, in the Fujitsu network, or not?
Actually, it is open source, so everyone
Now or future?
right now, Sunfish is version 0.3, and you can see the source code, but it cannot use for this primary CDI.
Yeah.
What are the actual limits of configuration? So how much servers you can implement, how much PCI boxes or PCI components?
Yeah. Right now, we have CDI V1, and it can attach compute node up to 10 servers, and we can connect fabric switch, 3 fabric switches, and each fabric switches have some PCI box. Okay, so
Will it be enlarged with
sorry.
version 2? Will that be enlarged?
Version 2 is sorry. Right now, I forgot the detailed number, but I will explain later. So CDI V2 CXL chassis has can include 10 CXL memories, and fabric switch can connect 8 CXL chassis. So you can add up to 80 terabytes of CXL memories.
But the CDIs whole RAID management, disk RAID management.
Disk.
Yes, for the RAID.
Actually, this system only don't support the RAID, but if you attach some disk system or software RAID system, you can use it.
Thank you.
How many GPUs will fit into this PCI boxes?
Right now, this box can contain 8 GPUs.
8 GPUs and
Yeah.
also 8 memory devices, right?
Yes.
Yeah.
But not combined or also mixed?
Yes. Yeah. CDI V2 user can connect both PCI fabrics and CXL fabrics, so user can use both devices.
You said each fabric switch can attach 8 of the PCI boxes, right?
Yeah.
3 switches in one system. That means,
Yes.
24
Yeah.
chassis.
That's right. Yeah. And CDI V2 system has a separate fabric switch, PCIe and CXL, separate fabric switches. But in CDI v3, a fabric switch can use PCIe Gen 6 and CXL 3.0. So user need to only one switch. Okay. Any other questions? Okay. Thank you very much.
Thank you.